Alright, so today is our first lesson on derivatives and tangent lines. The derivative, or the general idea of the derivative, is looking for the slope at a particular point. So we're able to get an idea of the slope between 2 points using the equation for slope, which is y2 minus y1 over x2 minus x1. Or in other words, the change in y over the change in x. Okay? So the issue is, if we're looking at the slope at a particular point, let's say we wanted the slope at this point right here, we'd have the change in y would be none, because there's only 1 point, and the change in x would be none, because there's only 1 point. So if we use that formula, we get 0 over 0, and as we talked about in our limits, that's an indeterminate form. So we need something else. So let's think of the slope between 2 points. Let's say we have 2 points here, this one and this one. That's the point 0, 0, that's the point 2, 4. So we have 4 minus 0 over 2 minus 0. Looks like a slope of 2 along that line. All right? Now, if we wanted to make that slope is probably an estimation, I would say, to the slope at one of these points here. Let's say it's the slope at this point. It's probably an estimation to it. But even if we compare our line, our blue line, to the red line, we see that those slopes don't really match up. So what would we need to do to make it more accurate of an estimation? Well, most of the time we just pick a closer point. So we go from here to here. So this is 4 minus 1 over 2 minus 1 gives us 3. Okay, a slope of 3. Now that looks more like it, but we'd have to keep getting closer and closer points until we found one that was infinitesimally close. So let's look at this in a formulaic way. We have f of, let's do this point and that point. F of 2 minus f of 1 over the change in x. Okay? Over the change in x. This is what we're looking at. This gives us the slope. Now, if we want this to be more accurate, we want this part right here to be pretty close. So let's rewrite this again. Let's say this is f of 1 plus the change in x minus f of 1 over the change in x. All right? Or in some cases, we might pick a different point, but this is the idea. The idea is that we want to go the change in x away from 1 and find the slope there. Now, with this equation, we can start to see how we might formulate the idea of a derivative at a point. If we want it to be as close to f of 1, that first point, as possible, then we want our change in x to be really close to 0. And we just had a whole unit dedicating to getting something really close to 0. We can make it a limit. So the limit as delta x approaches 0 of f of 1 plus delta x minus f of 1 over delta x. So now we're saying, okay, we want this slope formula when our change in x is getting really close to 0, or approaching 0. All right, so let's kind of work that out. This function, this f of x, is actually just x squared. So let's actually plug this in. Limit as delta x approaches 0 and we'll plug this into x squared, so 1 plus delta x squared, minus, then we'll plus this in, so 1 squared over delta x. And this looks like a limit problem we would have done last week. It's a multiply it out. So limit as delta x approaches 0 of 1 plus 2 delta x plus delta x squared minus 1 over delta x. Limit as delta x approaches 0 of the 1's will cancel and the delta x will cancel. So we have 2 plus delta x. And then we'll plug in 0 to that point and end up with 2. So this is saying our slope is 2. Well, if we look there, if I were to draw a line right here, a tangent line is what we call this, a line that touches it just at one point. If I were to draw a tangent line there, I would say that that slope looks about 2. Down 1, or down 2 over 1. That looks like it'd be a straight line to there. But maybe I'm wrong. Let's pick a point that we know the slope of. You should be able to look at this point right here and know the slope. If you don't, I question a little bit, but I mean, think about it. We have a pretty much flat line there. That should be a slope of 0. Let's use that same formula. We want f of 0 plus delta x minus f of 0. Oops. That should be minus f of 0. Okay, so we have f of 0 plus delta x minus f of 0 over delta x, where we want delta x approaching 0. All right, so let's solve this one out. We have, once again, the same f of x is x squared, so we have a limit as delta x approaches 0 of 0 plus delta x squared minus 0 squared over delta x. Limit as delta x approaches 0. This one should be much easier. It's just delta x squared minus 0. So really just delta x squared. Over delta x. The delta x's will cancel, so limit as delta x approaches 0 of delta x, and that equals 0. Hey, look, that's the slope we kind of assumed it was. It looks like it's a 0 slope. It got a 0 slope. So this is an idea we're going to run with. All right, we're going to take this idea of, okay, slope at a particular point. So I want you all to, you can on your own try to use this equation to figure out the slope at this point right here. You should be able to make some approximation of what it is, but use that same formula. Limit as delta x approaches 0 of, in this case, we're using x equals 1, f of 1 minus delta x minus f of 1 over delta x. And you can plug it in and solve it out. Okay? So I'll go ahead and do that. Hopefully you paused and worked it out on your own. Limit as delta x approaches 0 of negative and then 1 minus delta x squared plus 1 minus, and then if we just plug in 1 we get 0, so don't have to stress about that too much, over delta x. Limit as delta x approaches 0 of negative 1 plus 2 delta x minus delta x squared plus 1 over delta x. The 1 and the 1 will cancel, the delta x's will cancel. Limit as delta x approaches 0 plus delta x, which changes this to minus. Okay, fix that. So we'll simplify, the 1's will cancel, the delta x's will cancel, and we're left with negative 2 minus delta x. Plug in 0, and we end up with negative 2. If we look, that looks pretty close to a slope of negative 2. Can't be positive, but if I had to draw a straight line there, I'd pretty much say that that would be a slope of negative 2. Now, this whole idea can be expanded into a full function. We can take this concept and do it with a function. So let's take that same idea, but instead of doing a value for x, let's just use f of x. Oops. Plus delta x minus f of x over delta x. And let's use that same function we just did and plug it in there. So limit as delta x approaches 0 of negative x plus delta x squared plus 1 minus negative x squared plus 1. Okay, divided by delta x. And we'll simplify it all out. approaches 0 of negative x squared minus 2x delta x minus 1 plus x squared minus 1 over delta x. Oh, sorry, this should be plus 1, not minus 1. Oh, that's what I'm missing. I'm missing delta x squared. Ooh. So minus delta x squared, and then plus 1 plus x squared minus 1. All right, negative x squared and positive x squared will cancel. Plus 1 and negative 1 will cancel. Delta x, delta x, delta x will cancel. We should be left with limit as delta x approaches 0 of negative 2x minus delta x. And then we can plug in 0 to delta x and we get negative 2x. So this is a function that represents our slope at any given point. If we plug in 1, it'll give us the slope at 1. If we plug in 5, it'll give us the slope at 5. This is what is called the derivative. And so this is our formula for the derivative function. The limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. All right, so let's try that on a problem. Let's try that on this one right here. Limit as delta x approaches 0 of, well, it's f of x plus delta x, so we'll plug in x plus delta x to all the x's. Minus f of x, so just the function f of x, x squared minus 2x, all over delta x. All right, and then we're going to multiply all this out and simplify. It's going to be real long. I want you to just bear with it. So we have x squared plus 2x delta x plus delta x squared minus 2x minus 2 delta x minus x squared plus 2x, all of that over delta x. And now we'll simplify. Limit as delta x approaches 0. X squareds will cancel. The 2x will cancel. We're left with 2x delta x plus delta x squared minus 2 delta x. The delta x's will cancel. Cancel, 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 cancel. Limit as delta x approaches 0 of 2x plus delta x minus 2 as delta x approaches 0, so this is going to approach 0, so we end up with 2x minus 2. This is the equation of the derivative. So whatever x value we plug in here, right here, will give us the derivative or the slope at a point of this function. So if we plug in 1, it'll give us the slope at 1 on this function. If we plug in 5, it'll give us the slope at 5 on that function. Okay? We're going to skip a few problems because I'm not going to ask you to do every single one of these. So all of these are just different practice with this. The next thing, and really the last thing I think we're going to look at, is finding the equation of a tangent line. So the equation of a tangent line is the equation of a line at the point. Okay, equation for a line at the point. So we have this here, this equation, this function. We want the equation of the tangent line at x equals 4. Well, what three things do we need for an equation of a line? We need, well, if we write the equation of a line, we have y minus y1 equals m times x minus x1. So we need three things. We need a y value, we need an x value, and we need a slope. And we want the slope to be the slope at that point, or the derivative. Now, we want the derivative value, not the derivative equation. So we know the x, we're told x is equal to 4. We can find the y pretty easily by plugging it in. Y is just f of 4, which is 2. And then our slope, you could have found it on one of the previous problems. I'm just going to tell you what the equation is. Now, one thing I missed earlier is how we denote the derivative. The derivative is f prime of x, or you could say dy over dx. Either of these work. These both mean the same thing. So the derivative of this function is 1 over 2 squared of x. And you can go do the definition of derivative to prove that. Next lesson, I'll show you how to find that much quicker, but I'm just jumping ahead because I don't want to go through all that process. So this is our equation of the derivative. We have an x, we have y, we have a slope. Now, notice we're making an equation of a line. We want the slope at that point. So we don't want this. We want the derivative at the point 4. So we're going to plug in 4, 1 over 2 squared of 4, which gives us 1 over 4. So we have x, we have y, and we have slope. Let's plug it in. So y minus 2 equals 1 over 4, x minus 4. And we're not asked to simplify that. Okay? Next is the definition of differentiable. So differentiable at a point means the derivative can be found at that point. It has a slope. Differentiable function means that it is a continuous function where the derivative is also continuous. So where the derivative exists at all points. That leads us into this problem right here. Is this function differentiable at x equals 1? Well, the first question is it continuous at x equals 1? So we start by plugging in 1 to both of them and making sure they equal, similar to how we did continuity in the first unit. So we have x squared equals 3x minus 2. Plug in 1, we get 1 equals 3 minus 2, 1 equals 1. So it is continuous. All right, it's continuous. Now we need to check for differentiability. We need to find the derivative. Once again, you can go through the process of the definition of derivative to find this yourself, like we did earlier. I'm just going to go through and tell you that the derivative of the top one is 2x. The derivative of the bottom one is 3. So when x is less than or equal to 1, when x is greater than 1. And so now we want to find, is the derivative continuous? So we'll take them, set them equal. At x equals 1, well, when we plug in 1, we get 2 equals 3. That is not true, so it is not differentiable. It's continuous, but not differentiable. All right, I will see you all tomorrow. Let me know if you have any questions.